When scientists first looked deep into space, they expected to find a slowing universe. After all, gravity pulls everything together, so the expansion caused by the Big Bang should gradually fade. But what they found was the opposite. The universe was not slowing down. It was speeding up. In 1998, two teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, studied distant exploding stars called type EIA supernovae. These stellar explosions are bright enough to be seen billions of light years away and consistent enough to serve as standard candles, helping measure distance. When they compared the apparent brightness of those supernovae to how far their light had stretched, the data didn't add up. The galaxies hosting them weren't slowing under gravity. They were receding faster than models predicted. Something unseen was pushing them apart. At first, scientists questioned the data. Maybe the supernovae behaved differently in the early universe. Maybe interstellar dust dimmed the light. But after years of checks and cross-checks, the conclusion held: the universe's expansion is accelerating. This was not a small correction. It changed everything we thought we knew about cosmology. For decades, Einstein's equations of general relativity had suggested that gravity should slow cosmic expansion. But Einstein himself once added a cosmological constant, lambda, to balance his equations, thinking the universe was static. When Hubble discovered that the universe was actually expanding, Einstein called lambda his greatest blunder. Ironically, that same constant, the energy of empty space, might be exactly what drives today's acceleration. So, what could this mysterious energy be? It doesn't emit light, it doesn't absorb it, and it doesn't clump like matter. Yet it dominates the universe, making up nearly 70% of all its energy content. We call it dark energy. Dark energy isn't dark like shadows, it's dark because it's unknown. We infer its existence only through its effect, the way galaxies accelerate apart. In that sense, dark energy is the most powerful phenomenon we've never directly detected. Let's rewind for context. Right after the Big Bang, 13.8 billion years ago, everything was incredibly dense and hot. Matter, radiation, and gravity were locked in competition. Expansion slowed at first. Gravity tried to pull things back together. But billions of years later, dark energy began to dominate, overpowering gravity's pull. This transition happened roughly 5 billion years ago, around the time our Sun and Earth formed. Since then, the rate of expansion has kept increasing. That's why distant galaxies move away faster than nearby ones. Space itself is stretching. You might wonder, if space expands, why don't we expand with it? Why aren't atoms or solar systems stretching apart? Because dark energy acts only on vast cosmic scales. Gravity and electromagnetic forces hold smaller structures tightly together. So while galaxies drift apart, your coffee cup stays the same size. Expansion isn't an explosion in space. It's an expansion of space. The distance between galaxies increases even though neither moves through space like a rocket. The space between them grows. To picture it, imagine baking raisin bread. As the dough rises, the raisins move away from each other, not because they travel, but because the dough itself expands. In the cosmic version, galaxies are raisins, and spacetime is the dough. Once astronomers accepted that expansion is accelerating, the next challenge was measuring how fast. Using observations from the WMAP and Planck satellites, scientists mapped the cosmic microwave background, the afterglow of the Big Bang. It revealed the universe's precise geometry and composition. According to these maps, about 68% of the universe is dark energy, 27% dark matter, and only 5% normal matter. Everything we can see, stars, planets, people. That means most of reality is invisible to our senses. Dark matter pulls galaxies together. Dark energy pushes them apart. It's a cosmic tug of war, and dark energy is winning. The exact nature of dark energy remains one of the biggest open questions in physics. Is it Einstein's cosmological constant, an inherent energy of space itself? Or is it something dynamic, like a new quantum field slowly changing over time? Some models suggest a property called quintessence, a hypothetical energy field that varies with time and location. If quintessence is real, the fate of the universe could depend on how it evolves. We test these ideas by observing distant galaxies, supernovae, and the cosmic microwave background. Future missions like Euclid, ESA, and Nancy Grace Roman Telescope, NASA, aim to map cosmic acceleration in unprecedented detail. They'll measure how structures like galaxy clusters grow over time, revealing how dark energy influences cosmic evolution. If the data ever show that the rate of acceleration changes, it could mean dark energy itself changes, hinting at new physics. What's fascinating is how this discovery began with simple light. By studying the faint glow of dying stars, humanity uncovered a force shaping the destiny of everything. It's a reminder that the universe hides its biggest secrets in the smallest details. In 2003, the Nobel Prize in Physics honored the teams behind this revelation. Their work didn't just change astronomy, it reshaped our view of reality. For the first time, we realized the cosmos isn't coasting. It's accelerating into an unknown future. Today, cosmologists continue refining measurements using baryon acoustic oscillations and gravitational lensing. These methods test whether general relativity still holds at cosmic scales, or whether dark energy signals something deeper. The deeper we look, the more precise our data become, but also, the stranger the universe seems. Dark energy might be the key to unifying quantum physics and gravity, or the sign we're missing something entirely fundamental. Whatever it turns out to be, one thing is clear. This discovery was not an end, but a beginning. A door opened into a new era of cosmology, an invisible force, rewriting our understanding of space, time, and destiny. If we could somehow switch off dark energy, the universe would look very different. Galaxies would stop accelerating apart. Gravity would slowly pull everything back together. The night sky, billions of years from now, might even collapse into fire. But dark energy is doing the opposite. It's stretching the very fabric of spacetime faster and faster. And the more the universe expands, the more of this energy there seems to be. It's as if empty space itself creates more of itself as it grows. So where does it come from? One idea is that dark energy is simply the energy of empty space, what physicists call vacuum energy. Even in total emptiness, quantum mechanics says there's constant activity, virtual particles flashing into and out of existence. These fluctuations are small, but when summed over the vastness of space, they could add up to a powerful effect. This fits with Einstein's old cosmological constant, a term that represents energy inherent to space itself. However, there's a problem. If you calculate the predicted amount of vacuum energy from quantum theory, it overshoots the observed value by about 10 to the power of 120 times. That's a number so absurdly large, it's been called the worst prediction in physics. Clearly, something doesn't add up. Either our understanding of quantum fields is incomplete, or dark energy isn't vacuum energy at all. That's where new theories come in, each trying to explain the mystery from a different angle. The first major alternative is quintessence, a hypothetical dynamic field that changes over time. Unlike the cosmological constant, quintessence could evolve, causing the rate of cosmic acceleration to vary as the universe ages. If this field weakens, the universe's expansion might eventually slow. If it strengthens, space could stretch so violently that even atoms would be torn apart, a scenario scientists call the Big Rip. But quintessence is hard to test. To prove it, astronomers need to detect tiny deviations in how galaxies move or how light travels across billions of light years. That's why missions like Euclid, DESI, and Roman Space Telescope are designed to map cosmic acceleration with extreme precision. These surveys look for patterns known as baryon acoustic oscillations, faint ripples in the distribution of galaxies left from sound waves in the early universe. By tracking these ripples over time, scientists can see if the rate of expansion has changed. If dark energy truly evolves, its effects would differ in different epochs. For example, early galaxies might have clustered differently compared to modern ones. That's the fingerprint scientists are searching for, evidence that dark energy isn't constant but dynamic. Another theory suggests dark energy might not be a new force at all, but a sign that Einstein's gravity breaks down at cosmic scales. Maybe the equations of general relativity need an upgrade, new terms that only matter across intergalactic distances. This family of models is called modified gravity. They propose that what we think of as acceleration might simply be gravity behaving differently on enormous scales, bending and stretching space in unfamiliar ways. To test this, scientists use gravitational lensing, how light from distant galaxies bends as it passes massive objects. By comparing lensing patterns with expected values, we can check whether gravity acts as Einstein predicted. So far, general relativity still works beautifully, but the more precise our measurements become, the more we can push these theories to their limits. And if the data ever diverge, that could signal new physics waiting beyond the horizon. Some physicists explore another possibility, that dark energy might not be real at all. Maybe we misinterpret cosmic data. Perhaps we're seeing the result of cosmic inhomogeneities, uneven matter distribution making expansion appear faster than it is. But these models struggle to explain why the acceleration is so uniform across the sky. Every direction we look, galaxies recede at nearly the same rate, a strong clue that dark energy is indeed real and isotropic. Another piece of the puzzle comes from cosmic microwave background studies. Tiny fluctuations in that ancient light show how the universe's geometry curves. Measurements confirm it's remarkably flat, meaning there must be some kind of energy balancing everything out. Dark energy provides that balance. Without it, space would curve inward like a closed balloon, collapsing under its own weight. Instead, it remains almost perfectly flat, stretching forever. There's also an interesting link between dark energy and dark matter. Both are invisible, both interact mainly through gravity, and both dominate the universe. Yet they do opposite things. Dark matter binds, dark energy divides. Some researchers think they could even be connected, different aspects of a single unified phenomenon. Perhaps they're two sides of one cosmic coin we still don't fully understand. And beyond physics, dark energy has philosophical implications, not mystical, but scientific ones. It forces us to accept that most of existence is invisible and unexplained, yet measurable and predictable through mathematics. We've built instruments that can detect signals from billions of years ago, but we still can't explain the force shaping it all today. It's a paradox that drives modern cosmology. The better we measure, the more mysterious the universe becomes. To narrow down the options, cosmologists run massive computer simulations, digital universes evolving under different rules. Each model predicts slightly different galaxy distributions. We then compare those to real surveys like Sloan Digital Sky Survey or DES. The match so far: Einstein's lambda CDM model, lambda cold dark matter, still fits best. It's not perfect, but it describes the universe astonishingly well with just 6 parameters. Yet even this model hides tension. Different experiments measure slightly different expansion rates, a disagreement known as the Hubble tension. It might be the first real crack in our cosmic model. If the discrepancy persists, it could mean there's more to dark energy than we thought. Maybe a new field, particle, or hidden interaction at play. That's why the next decade of astronomy will be crucial. By 2030, we'll have enough data to map the universe's expansion history with unprecedented precision. We might finally tell whether dark energy is static, dynamic, or a symptom of something entirely new. Whatever the answer, one thing is certain: dark energy has forced physics to confront its limits. It challenges everything from quantum theory to relativity, reminding us how little we still know about reality itself. As we look ahead, one question remains: how will it all end? If dark energy stays constant, the universe will expand forever, galaxies drifting apart until their light fades into cold darkness, a scenario called the Big Freeze. If dark energy grows stronger, it could tear apart stars, planets, even atoms, the Big Rip. And if it weakens, gravity might win, pulling everything back into a final collapse, the Big Crunch. No matter the outcome, one truth endures. Understanding dark energy isn't just about predicting the end. It's about understanding why the universe is still moving at all. Every discovery brings us closer to answering the biggest question in science, not how it ends, but why it began.